Hello, and welcome to the Sleepy Scientist. If this is the kind of place where curiosity meets calm, take a moment to like the video, subscribe to the channel, and gently settle in. And if it feels right, leave a comment saying where this is being watched or listened to from. A quiet room, a late train, a darkened bedroom, or somewhere in between. It is a small detail, but in a universe where observation matters, even that choice becomes part of the story. Tonight's journey moves into the smaller scales nature allows, where the familiar rules of everyday life begin to loosen their grip. Quantum physics is often described as strange, confusing, or even impossible to picture. And yet, it quietly governs everything beneath the surface of ordinary experience. Every solid object, every breath of air, every distant star rests on these rules, even when they feel detached from intuition. This is not a race through equations or a test of memory. This is a slow unfolding. A careful look at how reality behaves when size shrinks, certainty fades, and probabilities replace solid answers. Here, particles act like waves. Outcomes depend on measurement, and the universe no longer promises simple explanations. The goal is not to resolve every mystery, but to understand what is known, what is uncertain, and why the world looks stable at all when its foundations are anything but. So let attention soften, let curiosity stay awake even as the body rests, and allow the quantum world to reveal itself at its own unhurried pace. Quantum mechanics is frequently presented in a way that creates confusion from the very beginning, so it helps to start by clearing away some common misunderstandings. It is not simply a framework for describing very small objects, nor is it a theory designed to be bizarre for its own sake. It is also not philosophy wearing the mask of physics. At its foundation, quantum mechanics is far more focused and far more practical. It is a formal system for calculating the results of experiments. That is the full extent of what it claims to do. A physical system is prepared in a controlled manner. Some property of that system is measured, and the theory provides the probabilities for the possible outcomes. No other scientific framework has ever matched quantum mechanics in this role. When applied properly, its predictions align with experimental results to an astonishing degree of accuracy. Confusion usually arises when a different kind of question enters the picture. What is the system really doing in the moments between measurements? What is taking place when nothing is being recorded? Here, intellectual honesty matters. Quantum mechanics, as a mathematical framework, does not attempt to answer those questions. It supplies a method for making predictions, not a detailed account of underlying physical reality. Whether such an account exists and what form it might take lies at the center of long-standing debates about interpretation. For now, it is best to remain anchored to what the theory demonstrably accomplishes. A useful way to approach quantum mechanics is through the sequence of preparation, measurement, and statistical analysis. Preparation involves setting up a system in a known condition. Atoms might be filtered so only those with a particular spin orientation are selected. A system might be cooled until it reaches its lowest possible energy. Light might be passed through a polarizing filter, so only certain orientations survive. However it is done, the aim is always the same: to place the system into a well-defined quantum state. Measurement then involves allowing the system to interact with a device that extracts information. A detector produces a signal, a current is registered, or a photon leaves a mark. Each measurement yields a definite outcome, typically represented by a numerical value. Statistics enter when this entire procedure is repeated again and again. Using the same preparation and the same measurement, the results vary from run to run. Over many trials they form a pattern. Quantum mechanics specifies exactly how that pattern should appear. All the additional structures commonly associated with quantum theory exist to carry out these calculations. The wave function, operators, and abstract mathematical spaces are computational tools, rather than extra claims about tangible objects. A key conceptual point is that the quantum state is not something that can be directly observed. It is not a misty substance filling space, nor is it a field that can be mapped point by point. Instead, it is a mathematical construct that encodes everything the theory allows you to say about future measurement outcomes. When the state appears to collapse during measurement, this need not be interpreted as a physical entity abruptly changing shape. It can be understood as an update to the predictive description once new information is acquired. Two foundational principles define the theory. The first is superposition. If a system is capable of occupying one state, and it is capable of occupying another, then it can also exist in a combination of both. The second principle is randomness in measurement outcomes. Measurements never reveal blended results. They always produce a single specific value, selected according to well-defined probabilistic rules. These rules are given by the Born rule, which connects probabilities to the squared sizes of mathematical amplitudes. This rule links smooth deterministic evolution with the sharp outcomes observed in experiments. It is extremely helpful to distinguish the formal mathematics of the theory from the interpretive narratives built around it. The equations and their predictive success are not controversial. The meanings assigned to them are. One can apply quantum mechanics effectively without adopting any particular interpretation, and in practice, many physicists do exactly that. Quantum behavior is not determined by scale, but by interference. When several possible processes exist and no physical information distinguishes between them, their amplitudes combine before probabilities are calculated. This can lead to results that differ dramatically from classical expectations. When interference is lost, typically through interaction with the surrounding environment, behavior becomes classical. This gradual suppression of quantum effects is described by decoherence. The term observer often creates more confusion than clarity. In quantum mechanics, an observer is simply any physical system capable of storing information in a stable form. A detector qualifies. A photographic plate qualifies. Conscious awareness plays no special role. The deeper question concerns how stable, definite records come into existence at all. Beneath everything lies a geometric framework. Quantum states inhabit a complex vector space known as Hilbert space. The degree of similarity between two states determines how easily one can be mistaken for the other. States that are completely distinct lie at right angles, while partially overlapping states are closer together. In this way, quantum mechanics is controlled by geometry. It is the angles between states, rather than any visual picture, that govern what can be predicted. Among all experiments associated with quantum mechanics, the double slit occupies a special place. It is often described as the theory's central demonstration, and that description is largely justified. Richard Feynman once suggested that it contained the only genuine mystery of quantum physics. That claim went too far, but it was not made lightly. If the double slit experiment is understood not merely as a curious pattern on a screen, but as a statement about how nature operates at a fundamental level, then much of quantum reasoning is already in view. The physical arrangement itself is straightforward. A source emits particles, which might be electrons, photons, or other quantum objects. These particles travel toward a barrier containing two narrow openings. Beyond the barrier sits a detection screen, whose role is simply to register where each particle arrives. If particles followed the expectations of everyday reasoning, each one would pass through a single opening, and over time the screen would show two broad accumulation regions aligned with the slits. That expectation fails. Instead of two simple bands, the screen displays a pattern of alternating bright and dark regions. Some locations receive many impacts, while others receive almost none. The pattern matches what would be produced by overlapping waves, where peaks reinforce one another and troughs cancel out. This behavior immediately signals that something more subtle than classical particle motion is taking place. The effect becomes even more revealing when the experiment is run at extremely low intensity. The source can be adjusted so that particles are emitted one at a time. At no moment is there more than a single particle moving through the apparatus. Each detection on the screen is localized and precise. There is no spreading, no partial arrival, only a single point appearing at a definite location. Initially, these points seem to appear without order, but as the process continues, still with particles arriving individually, a pattern slowly forms. After many thousands of detections, the same interference structure emerges, constructed dot by dot. Each particle lands in one place, yet the accumulated pattern reflects a structure that appears to require sensitivity to both slits at once. Quantum mechanics provides a clear rule for handling situations like this. When an outcome can occur through several alternatives that are physically indistinguishable, the theory requires that their amplitudes be combined before probabilities are computed. In the double-slit experiment, if no interaction anywhere records which opening the particle passes through, then the alternatives remain indistinguishable. The amplitude associated with one slit and the amplitude associated with the other are added together. Only after this combination is the probability determined. Depending on how the amplitudes align, the resulting probability can increase or decrease, giving rise to the alternating bright and dark regions on the screen. Everything changes once information about the path becomes available. If a detector is placed at a slit so that it can record whether a particle passes through, each arrival on the screen can now be linked to a specific route. As soon as this information exists physically, the interference pattern disappears. The screen fills in with two smooth bands, matching what classical reasoning would predict. This transition does not depend on awareness or dramatic disturbance. Even the gentlest detection mechanisms eliminate the interference. The pattern vanishes whether or not anyone checks the recorded data. What matters is not observation in the everyday sense, but the existence of information in the physical world. This distinction leads directly to an important conceptual divide. When alternatives cannot be distinguished by any physical record, the system is said to occupy a coherent superposition. In that regime, amplitudes interfere and produce non-classical effects. When alternatives become distinguishable, even in principle, the system behaves as a statistical mixture. Probabilities then add directly, and interference is lost. The gradual erosion of coherence through interactions with the surrounding environment is known as decoherence, and it explains why quantum behavior is rarely visible at macroscopic scales. Another critical ingredient is phase. Each amplitude carries a phase, and altering the relative phase between paths shifts the interference pattern across the screen. These shifts are measurable and predictable. Phase is therefore not a mathematical curiosity. It produces observable consequences and plays a central role in quantum dynamics. The experiment naturally invites a deeper question. What is the particle actually doing while travelling through the apparatus? Is it passing through both slits, one slit, or something entirely different? Quantum mechanics does not supply a definitive answer. It offers a framework for calculating outcomes, and those calculations work with remarkable precision. Various interpretations propose different narratives, but they all lead to the same experimental predictions. The equations themselves remain unchanged, regardless of the story chosen to accompany them. At the core of quantum mechanics lies a single mathematical object that quietly carries nearly all of the theory's explanatory strength. This object is known as the wave function, commonly labelled psi. Everything the theory can say about a physical system, everything it can successfully predict about future measurements, is contained within this single description. For a particle moving through space, the wave function depends on position and time. At every point it assigns a complex number. This number is not something that can be directly observed or measured on its own, but it plays a precise and indispensable role. When the squared magnitude of the wave function is evaluated at a particular location, it yields the probability density for detecting the particle there if a position measurement is performed. Where this value is large, detections are likely. Where it is small, detections are rare. It is tempting to picture this as a hazy cloud, marking where the particle truly exists, but that intuition quickly leads astray. The wave function is not a physical substance spread through space, and it is not a material object in any ordinary sense. It functions as a predictive framework. It specifies what outcomes can occur when a measurement is made and assigns precise probabilities to each possibility. One of the most conceptually challenging aspects of the wave function is that it takes complex values. These numbers possess both a size and a phase. It is natural to wonder why such mathematical complexity is required, and whether the theory might have been constructed using only real numbers. It cannot. Complex numbers are not optional embellishments. They are fundamental to how quantum mechanics works. Two wave functions can share exactly the same magnitude at every point in space, and still represent physically distinct states if their phases differ. Those differences manifest directly in interference phenomena. When amplitudes combine, their relative phases determine whether they reinforce or cancel one another. Without complex phases, interference would fail to match experimental results. Removing them would strip the theory of its predictive power. This reveals that the wave function encodes more than probability alone. The squared magnitude determines where a particle is likely to be found, but the phase governs how the state evolves over time and how it interacts with other states. Two wave functions that look identical when viewed only through their probability distributions can behave very differently as time passes. They may spread, interfere, or localize in distinct ways, even though a single measurement snapshot would not reveal any difference between them. Another essential point is that the wave function itself cannot be directly observed. There is no instrument capable of reading it off in a single measurement. Experiments instead access quantities derived from it, such as probabilities, expectation values, and correlations between measurements. Reconstructing a wave function requires preparing many identical copies of a system and probing them in different ways. This process, known as quantum state tomography, is possible but demanding. It requires careful control, repeated trials, and substantial data. Even then, the reconstructed state is defined only up to an overall phase, which carries no observable consequences. The form the wave function takes depends on how the system is described. This choice is called a basis. In the position basis, the wave function is written as a function of position. In the momentum basis, it is written as a function of momentum. These descriptions are related through a mathematical procedure known as a Fourier transform, which redistributes information between position and momentum in a precise and structured way. In the energy basis, the same state appears as a combination of energy eigenstates, each associated with a specific energy. None of these representations is more fundamental than the others. They are simply different ways of expressing the same underlying state. Choosing an appropriate basis can dramatically simplify a problem, much like selecting the right coordinate system can clarify a calculation in classical physics. A wave function that appears complicated in one description may look remarkably simple in another. All wave functions must satisfy an important constraint. Because the squared magnitude represents probability, and because probabilities must sum to 1, the total probability across all space must equal 1. This condition is known as normalization. It ensures that the wave function accounts for every possible outcome of a measurement. A wave function that is not normalized does not describe a physically allowable state until it is properly scaled. One of the most powerful consequences of the wave function structure follows directly from its linearity. If two wave functions each describe valid physical states, then any properly normalized linear combination of them also describes a valid state. This is the principle of superposition. The space of quantum states is linear, allowing new states to be formed by combining existing ones. It is crucial to understand what superposition does not mean. It is not a reflection of ignorance, and it is not the claim that a system secretly occupies one definite state or another while remaining unknown. A superposition is a genuinely distinct state with its own physical consequences, including characteristic interference patterns and time evolution. Treating superposition as mere uncertainty leads to predictions that conflict with experimental evidence. The contrast between superpositions and mixtures makes this clear. In a mixture, a system truly occupies one state or another, with probabilities assigned to each, but no phase relationships connect them. In a superposition, those phase relationships exist and matter. They allow amplitudes to interfere in ways that mixtures cannot reproduce. Given its central role, it is natural to ask what the wave function represents. Is it a real physical entity, like a field? Is it a bookkeeping tool that encodes information? Is it a description of knowledge, or something more fundamental? Quantum mechanics itself does not answer this. The formalism explains how to use the wave function to generate predictions, and it does so with extraordinary success. What the wave function means beyond that remains a question of interpretation. What is beyond dispute is how the wave function behaves. When no measurement is performed, it evolves smoothly and deterministically according to precise mathematical rules. This evolution preserves both normalization and superposition. When a measurement occurs, the predictions update abruptly to reflect newly acquired information. Reconciling these two modes of description remains one of the deepest, unresolved questions in the foundations of the theory. Despite its abstract character, the wave function is indispensable. Every interference pattern, every tunneling phenomenon, every stability feature of atoms relies on it. It carries the geometry, the probabilities, and the dynamics of quantum systems simultaneously. Learning to work with it requires letting go of classical intuitions about trajectories and replacing them with a framework built around structured possibilities. At first, this shift can feel unfamiliar and even unsettling. Classical physics emphasizes definite positions and velocities, evolving smoothly through time. Quantum mechanics replaces that picture with something quieter and more restrained. Instead of asking where a particle is, It asks what can be predicted about what will be observed if a measurement is made. The wave function provides that answer, expressed through complex numbers and geometric relationships. Once this perspective is accepted, many apparent paradoxes lose their sharpness. The wave function does not insist that reality be vague or mystical. It demands precision in prediction and care in accounting for how possibilities combine and interfere. It is less a picture of the world as it exists independently, and more a disciplined method for calculating what the world will allow to be observed. Applied consistently, that discipline is what gives quantum mechanics its enduring power. In quantum mechanics, measurable physical quantities are treated in a fundamentally different way than in classical physics. Position, momentum, energy, angular momentum and spin are not represented as simple numbers attached to particles. Instead, each measurable quantity is associated with an operator. An operator is a mathematical object that acts on the wave function and transforms it in a specific way. This change may seem subtle, but its implications are deep. In classical physics, measurement reveals a value the system already possesses. In quantum mechanics, measurement is inseparable from how operators act on states. The position operator acts by multiplying the wave function by position, while the momentum operator acts through differentiation with respect to position. These rules are not arbitrary choices. They are fixed by the requirement that the theory correctly matches experimental results. When an observable is measured, the possible outcomes are not arbitrary. They are specific values determined by the operator associated with that observable. These values are called eigenvalues. If energy is measured, only the energy eigenvalues of the energy operator can appear. No other outcomes are allowed by the theory. There is an immediate consequence of this structure. Measurement outcomes must always be real numbers. Imaginary energies or positions are never observed. To guarantee this, the operators representing observables must satisfy a mathematical condition. They must be Hermitian. Hermitian operators have two essential properties. Their eigenvalues are real, and their eigenstates associated with different eigenvalues are orthogonal. Orthogonality has a clear physical meaning. Orthogonal states are perfectly distinguishable. A measurement that identifies one can never be confused with the other. This ensures that different measurement outcomes correspond to genuinely distinct physical states. An eigenstate of an operator is a state in which the corresponding observable has a definite value. If a system is in an energy eigenstate, every energy measurement returns the same result. There is no randomness. Most quantum states, however, are not eigenstates of most observables. Instead, they can be written as superpositions of many eigenstates. When such a state is measured, one eigenvalue is obtained at random, with probabilities determined by how strongly the state overlaps with each eigenstate. This link between overlap and probability is given by the Born rule. To find the probability of a particular measurement outcome, one takes the overlap between the system state and the relevant eigenstate, then squares its magnitude. This rule is not derived from simpler ideas. It is a foundational postulate, and it is the point where mathematical structure becomes experimental prediction. Once probabilities are known, averages can be calculated. The expectation value of an observable is the average result obtained by repeating the same measurement many times on identically prepared systems. It is not a value that appears in a single measurement. Individual measurements always return eigenvalues. Expectation values describe long-run behavior, not single events. Some observables can be known simultaneously with complete certainty, while others cannot. Two observables are compatible if there exists a state in which both have definite values. This occurs when their operators commute, meaning the order in which they act does not matter. When operators do not commute, the observables are incompatible. There is no state in which both can be sharp at the same time. Position and momentum are the most familiar example. Their non-commutation leads directly to the uncertainty principle, which is a structural feature of the theory rather than a limitation of a measurement technology. So far, this description assumes ideal measurements, ones that are perfectly sharp and repeatable. Real experiments are often more complex. Measurements can be noisy, incomplete, or deliberately weak, providing only partial information. To describe such cases, quantum mechanics uses a more general framework known as generalized measurement theory. In this approach, measurements are described by sets of mathematical objects that still obey probability rules, but do not correspond to single sharp outcomes. This framework is essential in modern experiments and in quantum information science. Despite these refinements, the core ideas remain unchanged. Observables correspond to operators. Measurement outcomes correspond to eigenvalues. Probabilities are given by the Born rule. Expectation values describe averages, not individual results. Incompatibility arises from non-commuting operators, not experimental imperfections. What makes this framework so powerful is its universality. The same mathematical structure applies to atoms, light, electronic circuits, and quantum bits. The logic does not change from system to system, only the specific operators do. At first, this operator-based view can feel abstract, replacing familiar images with algebra and geometry. But it is precisely this abstraction that allows quantum mechanics to predict physical behavior with such extraordinary accuracy. The uncertainty principle is one of the most well-known ideas in quantum mechanics, and also one of the most frequently misunderstood. It is often described as a flaw in measurement, as if quantum systems appear uncertain only because experiments are imprecise or disruptive. That view is mistaken. The uncertainty principle has nothing to do with imperfect instruments or experimental disturbance. Even in an ideal world with flawless measurements, it would remain unchanged. What the principle describes is not a limitation of measurement, but a property of quantum states themselves. It places limits on the kinds of states that can exist. Certain pairs of physical quantities cannot both be sharply defined at the same time, regardless of how carefully they are measured. This restriction is built directly into the mathematical structure of the theory. The most familiar example involves position and momentum. Every quantum state has a spread in both quantities. These spreads can be quantified, and the uncertainty principle states that their product can never be made arbitrarily small. The spread in position multiplied by the spread in momentum is always bounded from below by a fixed constant. No quantum state ever violates this bound. As a result, a particle that is tightly localized in space must have a highly uncertain momentum. Its state necessarily contains a wide range of momentum components. Conversely, a particle with a very well-defined momentum must be spread out over a large region of space. There is no hidden loophole or clever way around this trade-off. It is tempting to imagine that the particle really possesses both a precise position and a precise momentum, and that the uncertainty reflects only ignorance. That intuition comes from classical physics. Quantum mechanics does not allow it. The uncertainty principle is not about what is unknown. It is about what cannot simultaneously exist. For position and momentum, the origin of this limitation is not mysterious. It arises from a mathematical relationship known as Fourier analysis. The description of a particle in position space and in momentum space are related by a Fourier transform. A function that is sharply localized in one representation must be spread out in the other. This is a general mathematical fact, not a peculiarity of physics. Quantum mechanics adopts this structure directly, turning a mathematical trade-off into a physical one. The uncertainty principle is not an extra assumption added to the theory. It emerges naturally from how quantum states are represented and related. The same logic applies beyond position and momentum. Any pair of observables whose operators do not commute will exhibit a similar limitation. The exact numerical bound depends on the observables involved, but the underlying principle is always the same. Spin provides a particularly clear illustration. For a particle with spin 1/2, measurements along different directions correspond to different operators. These operators do not commute. If the particle has a definite spin value along one direction, measurements along a perpendicular direction become completely unpredictable. There is no state in which both are simultaneously definite. This has nothing to do with experimental imperfection. It is a statement about the structure of allowed states. This shows why the uncertainty principle is not about hidden properties waiting to be revealed. The state itself lacks definite values for incompatible observables. Measurement does not uncover pre-existing precision. It produces outcomes consistent with the structure of the state. This represents a deep departure from classical intuition. In classical physics, uncertainty reflects ignorance. In quantum mechanics, for incompatible quantities, the theory does not permit sharply defined values to coexist. Reality is not vague, but it is organized differently than classical expectations suggest. Another common misunderstanding is the idea that uncertainty implies imprecision everywhere. In fact, quantum mechanics allows extraordinary accuracy. Atomic clocks, lasers, and quantum sensors all operate within the uncertainty principle and achieve remarkable precision. The principle limits simultaneous sharpness, not overall performance. The uncertainty principle also does not forbid precision outright. One quantity can be made very sharp, but only at the expense of another incompatible one. This trade-off can be controlled and exploited, which is exactly what modern quantum technologies do. Seen in this light, the uncertainty principle is not an obstacle, but a guide. It defines what is possible and what is not. It explains why classical descriptions fail at small scales and why quantum descriptions take their particular form. It is not a warning about the limits of science, but a statement about the structure of possibility in a quantum world. Between measurements, quantum mechanics is orderly and predictable. The quantum state does not jump or fluctuate at random. It evolves smoothly according to a single governing rule known as the Schrodinger equation, which describes how the wave function changes over time when no measurement is taking place. The meaning of this equation is straightforward. If the state of a system is known at one moment and its governing Hamiltonian is specified, then the future and past states are fully determined. There is no randomness in this process. Uncertainty enters only at the moment a measurement occurs. The Hamiltonian plays a central role in this evolution. It represents the total energy of the system, including both kinetic and potential contributions. In classical mechanics, it determines how a system moves through phase space. In quantum mechanics, it determines how the wave function evolves through Hilbert space. Alter the Hamiltonian, and the system's time evolution changes accordingly. The evolution generated by the Schrodinger equation has a special property known as unitarity. This guarantees that total probability is conserved. Probability may shift from one region to another or spread out over time, but it is never lost or created. Unitary evolution is also reversible. The equations allow the system's history to be traced backward just as easily as forward. There is no built-in arrow of time in the underlying dynamics. Unitarity also preserves the geometric relationships between states. The overlap between any two quantum states remains constant as they evolve. States that are initially perfectly distinct remain so, and states that partially overlap never change their degree of similarity. In geometric terms, time evolution acts like a rotation in the space of states, reshuffling them without distortion. Some states exhibit especially simple behavior under this evolution. Energy, eigenstates of the Hamiltonian maintain fixed probability distributions over time. The only change they undergo is a steady rotation of phase. Because measurable quantities depend on squared magnitudes, this phase evolution has no observable effect for an isolated energy eigenstate. Such states appear static, which is why they're called stationary. Most physical states are not energy eigenstates. They are superpositions of many such states, each evolving with its own phase. Over time, these differing phase evolutions lead to changing interference patterns. Motion, oscillation, and transitions all arise from the relative phases between energy components, not from the behavior of any single component alone. A clear example of quantum dynamics is the spreading of a wave packet. A wave packet may begin localized in space, resembling a particle at a definite position. But this localization is unstable. Because a localized state contains many momentum components, those components evolve at different rates. As time passes, the packet spreads out, even in empty space with no forces acting. This illustrates a fundamental point. A quantum particle is not a tiny object that naturally maintains its shape. Localization is fragile and must be sustained by interactions or confinement. Left on its own, a quantum state tends to spread. Despite this spreading, probability is always conserved. Quantum mechanics enforces this through the concept of probability current, which describes how probability density flows through space. Changes in probability density are exactly balanced by the flow into or out of a region, reflecting a continuity equation similar to those found in fluid dynamics. Probability moves, but it never vanishes. Up to this point, the theory is smooth, deterministic, and reversible. The difficulty appears when measurement enters the picture. Measurements produce random outcomes and irreversible records. Once a result is recorded, the system does not evolve smoothly back into a superposition of alternatives. This contrast lies at the heart of the measurement problem. The Schrodinger equation appears to govern all physical systems, yet measurement introduces behavior it does not describe. If measuring devices are treated as quantum systems and evolved according to the same rules, the combined system enters a superposition of all possible outcomes, each correlated with a different detector state. And yet experience reveals only one outcome, one pointer position, one recorded value. The other possibilities predicted by the mathematics do not appear directly. This is not a minor technical issue, but a deep conceptual tension. Either the Schrodinger equation is incomplete, or the emergence of a single outcome must be explained in a way consistent with underlying superposition. Different interpretations of quantum mechanics respond to this tension in different ways. What matters here is not which interpretation is correct, but where the problem arises. The conflict is internal to the theory itself. One set of rules describes smooth, reversible evolution. Another describes abrupt, irreversible outcomes. Both are essential. Understanding quantum time evolution makes this tension clearer, not weaker. Quantum mechanics is not imprecise or confused. It is exact, consistent, and extraordinarily successful. Its dynamics are continuous and deterministic. Its measurements are discrete and unpredictable. Holding both facts at once reflects the current state of the theory, not a failure to understand it. So far, quantum states have been described using wave functions. These describe what are known as pure states, and when a system is perfectly isolated and its preparation is fully known, this description is complete. Many real situations, however, are more complicated. In those cases, a single wave function is no longer sufficient, not because quantum mechanics fails, but because the available information is limited or shared. Sometimes the uncertainty is entirely classical. A system may be prepared in one state on some runs and a different state on others, with no way to know which occurred in a particular trial. In other situations, a system is entangled with something else. Even if the combined system has a well-defined quantum state, a single part of it cannot be described by a wave function alone. To handle all of these cases, quantum mechanics uses a more general object called the density matrix. The density matrix is a complete description of a quantum state. It contains everything needed to calculate measurement probabilities and expectation values, just like a wave function, but it can also represent mixtures and subsystems. For a pure state, the density matrix is built directly from the wave function and carries the same information, simply arranged in a different form. For a mixed state, the situation is different. A mixed state represents a system that is in one of several possible pure states, each with a certain classical probability. The density matrix is constructed as a weighted combination of the pure state density matrices. This averaging reflects genuine uncertainty rather than quantum superposition. One advantage of the density matrix formalism is that it treats pure and mixed states in exactly the same way. The same rules apply when calculating probabilities, averages, and time evolution, regardless of how the state arose. The difference lies in how much information the state contains. Pure states represent maximal information. Mixed states reflect missing or inaccessible information, either from classical uncertainty or from entanglement. This distinction can be quantified. One measure is purity, which equals 1 for a pure state, and is less than 1 for a mixed state. A deeper measure is entropy. Quantum mechanics uses the von Neumann entropy to quantify mixedness. Pure states have zero entropy, while mixed states have positive entropy that grows as information is lost or spread across entangled systems. The power of the density matrix becomes especially clear for composite systems. When a system consists of multiple parts, the full state may be known, but only one part may be accessible. To describe that part alone, the theory uses an operation called the partial trace. This removes the unobserved degrees of freedom and produces a reduced density matrix for the subsystem of interest. Crucially, even if the total system is in a pure state, the reduced state of a subsystem can be mixed. This occurs precisely when the parts are entangled. The mixedness of the subsystem does not reflect ignorance of the overall state. It reflects the fact that information is shared non-locally with the rest of the system. This leads to one of the central insights of quantum theory. Entanglement converts quantum correlations into what appears locally as classical randomness. The loss of access to part of an entangled system manifests as entropy and mixedness in the remaining part. For pure composite states, the amount of entanglement can be quantified by the entropy of the reduced state, known as entanglement entropy. The density matrix also cleanly distinguishes superpositions from mixtures. Two states may give identical probability distributions for a single measurement, yet differ fundamentally. Superpositions contain phase relationships that allow interference, while mixtures do not. In the density matrix, this difference appears in the off-diagonal elements. When those elements vanish, coherence and interference are lost. Decoherence can be understood naturally in this language. As a system interacts with its environment, entanglement spreads outward. Tracing over the environment turns the system's state into a mixed one. Coherence fades, interference disappears, and classical behavior emerges. No abrupt collapse is required. Information has simply flowed into degrees of freedom that are no longer tracked. Density matrices also describe real experimental conditions with ease. No system is perfectly isolated. Noise and uncontrolled interactions are always present. The density matrix framework allows these effects to be included without pretending the system remains in a perfectly known pure state. Time evolution fits naturally into this picture. In isolation, density matrices evolve in step with the Schrodinger equation. When measurements or environmental interactions are included, additional effects appear that describe loss of coherence and growing entropy. This unified treatment is one reason density matrices are indispensable in modern quantum mechanics. Mixed states are not flaws or approximations. They are an essential part of how the theory describes uncertainty, subsystems, and entanglement. The density matrix does not replace the wave function. It extends it. It is the language quantum mechanics uses when information is incomplete, shared, or distributed across entangled systems, which in practice is most of the time. If quantum mechanics truly governs everything, from subatomic particles to everyday objects, an obvious question follows. Why does the world appear so stable and classical? Why do familiar objects have well-defined positions, solid shapes, and continuous histories? Why is there no visible superposition of a mug being both on the table and on the floor at the same time? A crucial part of the answer lies in decoherence. It does not resolve every conceptual difficulty in quantum theory, but without it, the classical appearance of the world would be deeply puzzling. The key observation is that macroscopic objects are never isolated. A dust particle, a chair, or a living body is constantly interacting with its surroundings. Air molecules collide with it. Light scatters from its surface. Thermal radiation is emitted and absorbed. Countless weak interactions occur continuously without pause. Each interaction entangles the object with its environment. Information about the object's state spreads outward and becomes encoded in many external degrees of freedom. Because those environmental details are not tracked, the appropriate description of the object is no longer a pure quantum state. It becomes a reduced density matrix obtained by tracing out the environment. As this happens, a specific transformation occurs. The off-diagonal elements of the density matrix, which represent quantum interference between different alternatives, rapidly diminish in certain preferred descriptions. What remains is a state that behaves like a classical probability distribution over distinct possibilities rather than a coherent superposition. This process is known as decoherence. It does not rely on observers, measurements, or awareness. It is a purely physical consequence of entanglement with the environment. The larger and more interactive the environment, the faster decoherence takes place. Importantly, decoherence does not affect all descriptions of a system equally. The environment naturally selects particular states that are especially stable under interaction. These are called pointer states. Pointer states are the ones that persist despite constant environmental monitoring. For macroscopic objects, pointer states are usually states of definite position and orientation. Being here rather than there leaves robust and lasting traces in the environment. Light scatters differently. Air molecules rebound differently. Thermal radiation carries different information. These states are continually reinforced. In contrast, strange superpositions of being in multiple locations at once are extraordinarily fragile and are destroyed almost immediately. This explains why classical physics focuses on quantities like position and orientation rather than arbitrary superpositions. These classical variables are not chosen by convention or intuition. They are selected dynamically by environmental interaction. They are the states that remain stable. The timescales involved are extreme. For truly macroscopic objects, decoherence occurs incredibly fast. A microscopic dust grain in air loses coherence between different position states in a time span far shorter than anything that could be perceived or measured. By the time any observation could be made, coherence has already vanished. For microscopic systems, the situation is very different. An electron in a high vacuum, a photon trapped in an optical cavity, or a superconducting circuit cooled near absolute zero can remain coherent long enough for quantum effects to be observed and controlled. Much of experimental quantum science is devoted to isolating systems precisely to slow down decoherence. Decoherence explains why interference between large-scale alternatives is never seen. It explains why the world appears classical, even though its underlying laws are quantum. It shows how classical probability emerges naturally from quantum theory once environmental interactions are taken into account. But it is important to be precise about its limits. Decoherence does not explain why a single outcome is experienced. After decoherence, multiple alternatives still exist in the mathematical description, each with its own probability. Decoherence suppresses interference between them, but it does not select one outcome and discard the others. That remaining question belongs to the measurement problem. Different interpretations of quantum mechanics propose different resolutions, but decoherence itself remains neutral. It does not favor collapse, branching worlds, hidden variables, or any other interpretation. This neutrality is a strength. Decoherence is not an interpretive add-on. It is a physical process that occurs regardless of how quantum mechanics is interpreted. What decoherence provides is a bridge. It connects the smooth, deterministic evolution of quantum states with the stable, classical patterns observed in everyday life. It shows that the classical world is not an exception to quantum rules, but a natural consequence of living in a universe where no system is ever truly isolated. Entanglement is one of the features that most clearly separates quantum mechanics from every classical theory that came before it. It is not simply a matter of correlation, and it is not just a reflection of ignorance about hidden details. Entanglement is a situation in which multiple systems must be described together because none of them possesses its own independent quantum state. In classical physics, even when two objects interact strongly, it is always possible, at least in principle, to assign each one its own complete description. In quantum mechanics, this is not always true. Two systems are said to be entangled when their joint state cannot be written as a product of separate states for each system. The whole exists, but the parts do not, at least not in the usual sense. Any attempt to describe one system by itself necessarily leaves something out. This distinction matters because entanglement produces correlations that are stronger than anything classical physics allows. These correlations persist no matter how far apart the systems are, as long as they remain entangled. And it was precisely this feature that troubled some of the founders of quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument that has become known as the EPR paradox. Their goal was not to reject quantum mechanics outright, but to show that it could not be a complete description of reality. Their reasoning was careful and subtle. Imagine two particles prepared in an entangled state, and then separated by a large distance. By measuring one particle, it becomes possible to predict the result of a corresponding measurement on the other particle with certainty. Crucially, this prediction can be made without physically interacting with the distant particle at all. Einstein, Podolsky, and Rosen argued that if a physical quantity can be predicted with certainty without disturbing the system, then that quantity must correspond to an element of reality. They also assumed locality, meaning that physical influences cannot travel faster than light. Taken together, these assumptions seem to imply that the distant particle must already possess definite values for the measured properties, even before any measurement is performed. Quantum mechanics, which does not assign such definite values, therefore appeared incomplete. For decades, this remained a philosophical debate. Quantum mechanics worked, but the discomfort lingered. Then, in 1964, John Bell changed the situation completely. Bell showed that the assumptions behind the EPR argument could be tested experimentally. He proved that any theory that reproduces the predictions of quantum mechanics while also maintaining locality and pre-existing values must satisfy certain statistical constraints. These constraints are known as Bell inequalities. Quantum mechanics predicts that entangled systems will violate these inequalities under the right measurement conditions. Bell did not merely suggest this. He derived specific mathematical limits that local hidden variable theories cannot exceed. If experiments violated those limits, then no theory based on both locality and pre-assigned values could be correct. One particularly practical version of these constraints is known as the CHSH inequality. It involves measuring pairs of entangled particles with different settings on each side and comparing the correlations between the results. The inequality sets a clear numerical bound that any local hidden variable theory must obey. Experiments were eventually performed, beginning in the 1970s and becoming increasingly refined over time. The results were unambiguous. Bell inequalities are violated. The correlations predicted by quantum mechanics are observed in the laboratory. These violations persist even when experiments are designed to close potential loopholes related to detection efficiency and communication delays. The conclusion is unavoidable. Nature does not obey the combined assumptions of locality and pre-existing measurement values. At least one of them must be abandoned. This does not mean that quantum mechanics allows faster-than-light communication. That is an important and often misunderstood point. Although entangled systems exhibit correlations that cannot be explained by local mechanisms, they do not allow information to be transmitted instantaneously. If two observers, traditionally called Alice and Bob, share an entangled pair and perform measurements on their respective particles, the outcomes each observer sees locally are completely random. Alice cannot choose a measurement setting that forces Bob's result to change in a controllable way. Bob's statistics do not depend on what Alice does. Only when Alice and Bob later compare their results do the correlations become apparent. This property is known as no signaling. It ensures that quantum mechanics remains compatible with special relativity, at least at the level of observable communication. The non-locality revealed by Bell's theorem is subtle. It resides in correlations, not in signals or causal influence that could be used to send messages. Quantum mechanics is therefore non-local in a specific sense. The joint behavior of entangled systems cannot be reduced to local explanations involving independent parts with predefined properties. But it is not non-local in the sense of violating relativistic causality. Entanglement also forces a reconsideration of how properties are assigned to systems. In classical thinking, it is natural to assume that physical quantities have definite values, whether or not they are measured. Quantum mechanics challenges this assumption, and Bell's theorem shows that it cannot be maintained in a simple, local way. This challenge is pushed even further by a result known as the Cauchy-Specker theorem. This theorem applies to quantum systems with 3 or more dimensions in their state space. It shows that it is impossible to consistently assign definite values to all observables in a way that is both non-contextual and compatible with quantum predictions. Non-contextual means that the value assigned to a measurement does not depend on which other compatible measurements are performed alongside it. The Cauchy-Specker theorem demonstrates that such assignments cannot exist. The outcome of measurement cannot be thought of as revealing a value that was already there independent of context. Instead, measurement outcomes depend on the full experimental arrangement. This idea, known as contextuality, is deeply woven into quantum mechanics. It means that the properties of a system are not merely uncovered by measurement. They are defined within a framework that includes how the measurement is performed. Context matters. Taken together, entanglement, Bell inequality violations, and contextuality paint a consistent picture. Quantum mechanics does not describe a world made of independent parts carrying pre-assigned properties. It describes a world in which correlations are fundamental, in which the whole can be more than the sum of its parts, and in which measurement outcomes cannot always be traced back to hidden local facts. This does not imply chaos or inconsistency. The rules of quantum mechanics are precise and well tested. The strangeness lies not in unpredictability, but in the structure of what is being predicted. Entanglement is not a curiosity confined to thought experiments. It is routinely created and measured in laboratories. It is the resource behind quantum computing, quantum cryptography, and quantum teleportation. These technologies do not exploit faster than light communication. They exploit the deep, non-classical structure of quantum correlations. Perhaps the most important lesson of entanglement is this. Quantum mechanics does not merely revise our understanding of motion or energy. It revises our understanding of separateness. Systems that appear distinct can share a single quantum description. What happens to one can be correlated with what happens to another in ways that defy classical explanation without violating causality. This is not a flaw in the theory. It is one of its most precisely confirmed features. And it is a reminder that intuition built from everyday experience is not always a reliable guide to the deeper structure of reality. Quantum mechanics does not ask us to abandon logic. It asks us to expand it. Quantum mechanics is unusual in that it works extraordinarily well while remaining conceptually unsettled. Every interpretation of the theory agrees on the mathematics and on the experimental predictions. No experiment performed so far has been able to distinguish between them, and yet physicists and philosophers continue to argue about what the theory is actually saying about the world. From a purely practical point of view, this might seem unnecessary. The equations work. The predictions are accurate. One can calculate energy levels, scattering rates, and interference patterns without ever committing to a story about what is really happening. This attitude is often summarized with the phrase, "shut up and calculate." But for many people that is not satisfying. Physics has always been about more than prediction. It has also been about understanding. Interpretations matter because they attempt to answer questions that the formalism itself leaves open. What is a quantum state? What does measurement do? Is randomness fundamental or only apparent? What kind of world must exist for these rules to be true? Different interpretations give different answers to those questions, even though they agree on what experiments will show. The interpretation most people encounter first is usually called Copenhagen, although that name hides more than it reveals. It is not a single, sharply defined position, but a loose collection of views associated with figures like Niels Bohr and Werner Heisenberg. At its core, the Copenhagen approach emphasizes the limits of description. Quantum systems are described using classical concepts such as position, momentum and measurement apparatus, but these concepts cannot all be applied at the same time. This idea is known as complementarity. Certain descriptions exclude others, not because of technical limitations, but because the concepts themselves are mutually incompatible in the quantum domain. In this view, the wave function is not a picture of physical reality. It is a tool for predicting the outcomes of measurements. Asking what the system is doing between measurements is regarded as a category error. The theory tells you what you can say about observations, not what exists independently of them. This stance avoids many paradoxes by refusing to engage with them. Its strength is its restraint. Its weakness is that it leaves many people feeling that something important has been left unsaid. A very different approach was proposed in 1957 by Hugh Everett. In what is now called the many worlds interpretation, the wave function is taken completely seriously. It is not a mere bookkeeping device. It is the full description of reality, and it always obeys the Schrodinger equation. There is no collapse. When a measurement occurs, the measuring device and the observer become entangled with the system. All possible outcomes occur, each in a different branch of the wave function. From the inside, an observer experiences only one outcome, because the branches no longer interfere. From the outside, the evolution is smooth and deterministic. This interpretation has a certain elegance. It removes the special role of measurement and treats all physical processes uniformly, but it raises difficult questions of its own. Why should probabilities follow the Born rule if all outcomes occur? What exactly defines a branch? And how should one think about the enormous proliferation of unobservable worlds implied by the theory? Some find this picture compelling, others find it excessive. Another interpretation takes a more classical turn. Bohmian mechanics, also known as pilot wave theory, introduces additional structure beneath the standard formalism. In this approach, particles always have definite positions. They move along well-defined trajectories, guided by the wave function through a specific equation of motion. The wave function itself still evolves according to the Schrodinger equation, but it no longer represents the full state of the system. The complete description includes both the wave function and the actual particle positions. Measurement outcomes are determined by these positions. The apparent randomness of quantum mechanics arises because the initial positions are unknown in practice. Bohmian mechanics reproduces all the predictions of non-relativistic quantum mechanics, but it does so at a cost. The guiding equation is explicitly non-local. The motion of one particle can depend instantaneously on the configuration of distant particles. Extending the theory to relativistic quantum field theory is possible in limited forms, but it is technically and conceptually challenging. Even so, Bohmian mechanics demonstrates that quantum phenomena do not logically require indeterminism, only non-locality. Some interpretations take a more radical step and modify the theory itself. Collapse models propose that the Schrodinger equation is not exact. Instead, it is supplemented with a stochastic process that causes the wave function to localize spontaneously. One well-known example is the Ghirardi-Rimini-Weber model. In this framework, individual particles undergo random collapses extremely rarely. For microscopic systems, these events are negligible, but for macroscopic objects composed of enormous numbers of particles, collapses happen constantly, forcing the wave function into localized states very quickly. These models have a clear advantage. They solve the measurement problem directly. There is only one outcome, and it is selected dynamically. They also make predictions that differ slightly from standard quantum mechanics, which means they can be tested experimentally. Their main drawback is that the collapse mechanism appears somewhat ad hoc. Additional parameters must be introduced, and the underlying physical motivation remains unclear. There are also interpretations that shift the focus away from absolute descriptions. Relational quantum mechanics suggests that the properties of a system are only defined relative to other systems. There is no single observer-independent state of the universe. What is real depends on the relation between systems, not on a global description. The consistent histories approach takes yet another angle. Instead of focusing on measurements, it assigns probabilities to entire sequences of events, called histories. These histories must satisfy specific consistency conditions to avoid interference. Within this framework, questions about what happened can be meaningful, but only within a carefully defined set of histories. Cubism or quantum Bayesianism pushes subjectivity further. In this view, the wave function does not describe the world at all. It represents an agent's personal expectations about future experiences. Measurement outcomes are real experiences, but the probabilities assigned to them are expressions of belief, updated using rules similar to Bayesian inference. This interpretation reframes quantum mechanics as a tool for decision-making rather than a description of objective reality. Each of these interpretations emphasizes different aspects of the theory. Some preserve determinism at the cost of non-locality. Some preserve locality at the cost of abandoning pre-existing properties. Some modify the dynamics. Some deny that the wave function is an objective thing at all. What they all share is agreement on predictions. No experiment performed so far can tell them apart. This is both a strength and a frustration. It means quantum mechanics is internally consistent and extraordinarily robust. It also means that our deepest questions about what the theory says about reality remain open. This situation is unusual in physics, but it is not unprecedented. In the past, debates about the nature of space, time, and gravity persisted long after the relevant equations were known. Eventually, new experiments or new theoretical insights shifted the landscape. For now, interpretations serve as conceptual lenses. They shape how people think about quantum mechanics, how they teach it, and how they attempt to extend it. They influence intuition, even when they do not influence calculation. Whether interpretations ultimately reflect something deep about the universe, or simply different ways of organizing the same information, is still unclear. What is clear is that quantum mechanics forces a separation between prediction and explanation that is uncomfortable but unavoidable. The theory tells us, with unmatched precision, what will happen when we perform experiments. What it does not tell us, at least not uniquely, is how to imagine the world that gives rise to those outcomes. And perhaps that tension is not a flaw, but a clue. Spin is one of the places where quantum mechanics most clearly breaks from everyday intuition. It is a form of angular momentum that particles possess intrinsically. It does not come from anything rotating in space, and it cannot be understood by imagining a tiny object spinning like a top. An electron, for example, has spin 1/2. That number is not a speed, a size, or a rotation rate. It is a label that tells you how the electron behaves under rotations and how it responds to magnetic fields. Trying to picture spin as literal motion leads to contradictions almost immediately. If an electron were a tiny spinning ball, its surface would have to move faster than light. Nature is not doing that. Spin is a purely quantum property. Spin was revealed experimentally in a striking way through the Stern-Gerlach experiment. a beam of silver atoms was sent through a magnetic field that varied in strength from one place to another. Classically, one would expect the magnetic moments of the atoms to point in random directions, producing a continuous smear on a detector. That is not what happened. Instead, the beam split cleanly into two distinct parts. There were not many possible deflections, there were exactly two. This result showed that the angular momentum associated with the atoms was quantized. It could take only specific values when measured along a given direction. Spin was not a hidden classical variable. It was something fundamentally discrete. Behind this discreteness lies a powerful mathematical structure. Angular momentum in quantum mechanics is described by operators that obey specific relationships with one another. These relationships are called commutation relations, and they encode how different components of angular momentum interact. Written out in words, the key relation says this: the commutator of the x component of angular momentum with the y component equals I times h bar times the z component, and the same pattern holds when the roles of the axes are cycled. These relations are not assumptions added by hand. They follow from the symmetry of space itself. From these relations alone, one can derive an extraordinary result. Angular momentum cannot take arbitrary values. Its allowed magnitudes come in discrete steps labelled by a number traditionally called j. That number can be 0, 1/2, 1, 3/2, 2, and so on. There are no values in between. Nature skips them entirely. Among all these possibilities, the simplest non-trivial case is spin 1/2. This is the case for electrons, protons, and many other fundamental particles. The quantum state of a spin 1/2 system lives in a two-dimensional space. There are only two possible outcomes when spin is measured along any chosen axis. Along a given direction, often labelled vertical for convenience, the outcomes are usually called up and down. But these labels should not be taken literally. They're shorthand for two distinct measurement results, not tiny arrows pointing in space. Along a different direction, such as horizontal, the same particle can again give two outcomes, which are different combinations of the previous ones. What makes spin especially interesting is that a state that is definite along one axis is generally not definite along another. A particle that is certainly spin up along the vertical axis will give completely unpredictable results when measured along a perpendicular axis. This is another expression of incompatible observables and non-commuting operators. Mathematically, the spin operators for a spin 1/2 system can be represented using a set of simple matrices known as the Pauli matrices. These objects capture all the algebraic properties of spin and make calculations manageable. Physically, they describe how the state responds to measurements and to magnetic fields. Because spin 1/2 systems have exactly two distinguishable states, they have become central to modern quantum technology. In quantum information science, such a system is called a quantum bit, or qubit. Unlike a classical bit, which is either 0 or 1, a qubit can exist in superpositions of its two basic states, with phases that matter. This ability underlies quantum computation and quantum communication. To visualize the states of a spin 1/2 system, physicists often use a geometric picture called the Bloch sphere. In this picture, every pure quantum state of the system corresponds to a point on the surface of a sphere. One pole of the sphere represents spin up along a chosen axis, often taken to be vertical. The opposite pole represents spin down along the axis. Points around the equator represent equal superpositions of up and down, differing only in their relative phases. Every possible pure state appears somewhere on the surface. This picture is more than a drawing, it reflects real structure. Any unitary evolution of a spin 1/2 system corresponds to a rotation of this sphere. Applying a magnetic field, for example, causes the state vector to move smoothly around the sphere, tracing out a path that reflects the system's dynamics. Mixed states have a natural place in this picture as well. Instead of lying on the surface, they appear as points inside the sphere. The closer a point is to the center, the more mixed the state is. The very center represents complete randomness, where all measurement outcomes are equally likely and no coherence remains. The Bloch sphere provides a rare example in quantum mechanics where an abstract mathematical object can be represented in a simple, intuitive geometric way without losing accuracy. It makes clear how superposition, phase, measurement, and dynamics fit together in a single coherent structure. Spin also illustrates an important lesson about measurement. Measuring spin along one axis does not reveal a pre-existing vector pointing in space. It creates an outcome consistent with the quantum state and the measurement context. Change the measurement axis, and you are asking a different question of the same system. This contextual nature of spin measurements is not a flaw. It is a feature. It reflects the deep connection between symmetry, measurement, and information in quantum mechanics. Spin is not about hidden rotation. It is about how quantum systems respond to being probed. From atomic structure to magnetic resonance imaging, from particle physics to quantum computing, spin plays a central role. Its algebra dictates selection rules. Its quantization stabilizes matter. Its two-level structure enables entirely new kinds of technology. And yet, despite its importance, spin remains quietly abstract. It does not invite mechanical pictures. It resists visualization as motion. It simply obeys its rules, with extraordinary consistency. Spin is a reminder that quantum mechanics does not always replace classical ideas with more complicated versions. Sometimes it replaces them with entirely different concepts. Angular momentum without rotation is one of those replacements. Understanding spin means accepting that not every property needs a classical analog to be real. Some properties exist because the maths allows them and the experiments demand them. In the quantum world, that turns out to be more than enough. One of the quiet strengths of quantum mechanics is how deeply it connects structure to behavior. Certain patterns are not accidents. They are enforced by symmetry. And whenever a symmetry exists, something else follows with remarkable reliability. A quantity is conserved. This connection was first made precise by Emmy Noether in the context of classical physics, but it carries over seamlessly into quantum mechanics. The idea is simple to state, even if its implications are far-reaching. Every continuous symmetry of a system corresponds to a conserved quantity. In quantum mechanics, this relationship has a very clean expression. If an observable commutes with the Hamiltonian, then its expectation value does not change with time. In other words, that quantity is conserved during the system's evolution. This is not a rule added on top of the theory. It falls directly out of the structure of time evolution. There is also a complementary way to see the same connection. Observables do not just label measurable quantities, they also generate transformations. Momentum generates translations in space. Angular momentum generates rotations. Energy generates time evolution. The operators associated with conserved quantities are the generators of the symmetries themselves. This dual role is one of the reasons quantum mechanics feels abstract at first. The same mathematical object both represents what you can measure and determines how states change when symmetries are applied. Consider spatial translation. Imagine a system where the laws of physics are the same everywhere. There is no preferred location. This property is called translation invariance. If the Hamiltonian does not depend explicitly on position, then the system has this symmetry. In such a system, momentum is conserved. A particle's average momentum does not change with time unless something breaks the symmetry, such as an external force or a boundary. Momentum also plays the role of generator of translations. Acting on a wave function with the appropriate transformation shifts it in space. The effect can be described as follows. Applying the exponential of I times the momentum operator multiplied by a displacement and divided by h bar moves the wave function rigidly by that displacement. Nothing else changes. The shape remains the same, only its location is different. This is not a metaphor. It is an exact statement. The mathematical operation that defines momentum is precisely the one that produces spatial translations. Conservation of momentum and uniformity of space are two sides of the same coin. Rotation works in an analogous way. If a system looks the same after being rotated, then it has rotational symmetry. If the Hamiltonian is unchanged under rotations, angular momentum is conserved. This symmetry is especially clear in systems governed by central forces, where the interaction depends only on distance from a center and not on direction. The hydrogen atom is a classic example. The electrostatic force between the proton and the electron depends only on how far apart they are, not on the orientation of the atom in space. As a result, angular momentum is conserved. Angular momentum operators generate rotations. Acting on a quantum state with the appropriate rotation operator produces a new state that is rotated in space. The underlying algebra of angular momentum operators mirrors the algebra of infinitesimal rotations in three-dimensional space. This is not coincidence. It is the mathematical expression of rotational symmetry. Because rotations can be performed about different axes, the components of angular momentum do not commute with one another. This non-commutation is not a flaw. It reflects the geometry of space itself. Rotations about different axes do not commute either. Doing one rotation and then another generally gives a different result than doing them in the opposite order. Energy fits naturally into this pattern as well. Time translation symmetry corresponds to energy conservation. If the Hamiltonian does not depend explicitly on time, then the energy of the system is conserved. Energy generates time evolution in the same sense that momentum generates spatial translation. Acting with the appropriate operator moves the state forward in time. These ideas may sound abstract, but they have very concrete consequences. One of the most important is the existence of selection rules. Selection rules determine which transitions are allowed and which are forbidden. They do not rely on detailed calculations of forces or trajectories. They follow directly from symmetry. When a system undergoes a transition, such as an atom emitting or absorbing light, the probability of that transition depends on a quantity known as a matrix element. This matrix element involves the overlap between the initial state, the final state, and the operator that mediates the interaction. If a transition would violate a conservation law implied by symmetry, that matrix element is exactly zero, not small, not unlikely, zero. The transition cannot occur. This is why certain spectral lines appear and others do not. It is why atoms emit light at specific frequencies with specific polarization patterns. It is why entire classes of processes are forbidden, regardless of how much energy might be available. In atomic physics, electromagnetic transitions provide a clear example. The interaction between light and matter respects rotational symmetry and certain spatial reflection symmetries. As a result, angular momentum cannot change arbitrarily when an atom emits or absorbs a photon. For electric dipole transitions, which are the most common, the total angular momentum of the atom must change by no more than 1 unit. Transitions that would require a larger change are forbidden. In addition, a property known as parity must flip. States that are symmetric under spatial inversion can only transition to states that are antisymmetric, and vice versa. These rules are not empirical accidents. They follow from the symmetry properties of the electromagnetic field and how it couples to charged particles. Once the symmetry is specified, the selection rules are fixed. Symmetry also explains degeneracy, the phenomenon where multiple distinct quantum states share the same energy. When a system has a symmetry, states related by that symmetry must have the same energy. In a rotationally symmetric system, states with different orientations but the same total angular momentum are energetically equivalent. Breaking a symmetry lifts degeneracy. Apply an external magnetic field and a rotational symmetry is reduced. Energy levels split. This effect, known as the Zeeman effect, is not mysterious. It is symmetry breaking made visible. What makes symmetries especially powerful is that they allow strong conclusions without detailed knowledge of the dynamics. One does not need to solve the full equations of motion to know that momentum is conserved in free space, or that certain transitions are forbidden in atoms. Symmetry alone is enough. Quantum mechanics elevates this idea further by embedding symmetry directly into its formal structure. Operators generate transformations, commutation relations encode geometry. Conservation laws emerge as statements about what does not change as states evolve. This perspective also clarifies why conservation laws sometimes appear to fail in measurements. When a system interacts with a measuring device or environment, the symmetry of the subsystem alone may be broken, even if the symmetry of the total system is preserved. Momentum might not be conserved for the particle by itself, but it is conserved for the particle plus apparatus together. The bookkeeping must include everything involved. Seen this way, conservation laws are not fragile rules that can be violated by observation. They're global constraints that apply to closed systems. Apparent violations usually signal that something has been left out of the description. Symmetry thinking also prepares the ground for more advanced ideas. Gauge symmetries, internal symmetries, and space-time symmetries all play central roles in modern physics. Quantum mechanics provides the language in which these S. At a deeper level, symmetries tell us what questions make sense to ask. They limit the possible forms of laws. They determine what can change and what must remain the same. In a theory where measurement outcomes are probabilistic, symmetry provides a rare source of certainty. When a symmetry exists, something is protected. A quantity cannot drift. A transition cannot occur. A pattern must repeat. This is why symmetries are not merely aesthetic features. They are structural constraints. They shape the space of possibilities before any calculation begins. In quantum mechanics, this role is especially stark. The theory does not start with forces and trajectories. It starts with states and transformations. Symmetry tells you which transformations matter and which quantities survive them unchanged. Once that is understood, conservation laws stop feeling like separate principles and start feeling inevitable. They are not rules imposed on nature. They are consequences of how nature allows itself to be transformed without changing its identity. And that, quietly, is one of the deepest lessons quantum mechanics has to offer. Quantum information takes the ideas of quantum mechanics and treats them not as curiosities, but as resources. Instead of asking only what a system is doing, it asks what information the system can carry, how that information can be transformed, and what the laws of physics allow or forbid. At the heart of this approach is the qubit. A qubit is the quantum analogue of a classical bit. Like a classical bit, it has two distinguishable states. But unlike a classical bit, a qubit is not restricted to being in one state or the other. It can exist in a superposition of both at once, with a relative phase that matters. This difference is not just philosophical, it has practical consequences. A qubit can interfere with itself. Multiple qubits can become entangled, forming joint states that cannot be reduced to independent parts. These features give quantum information its distinctive power and also its fragility. One of the first surprises in quantum information theory is something called the no-cloning theorem. It states that it is impossible to make a perfect copy of an unknown quantum state. This is not a matter of insufficient technology or experimental noise. It is a mathematical impossibility built into the structure of quantum mechanics. The reason is subtle but fundamental. Copying a state would require a physical process that takes one unknown input state and produces two identical outputs, regardless of what that input state is. Such a process would have to preserve inner products between states. Quantum mechanics does not allow this to be done universally. Attempting to clone would inevitably disturb the state or fail to copy it accurately. This limitation has deep implications. Quantum information cannot be backed up the way classical information can. There is no perfect quantum photocopier, but the same restriction also enables new forms of security. An eavesdropper cannot intercept and copy quantum information without leaving traces. Any attempt to extract information unavoidably disturbs the state. This idea is central to quantum cryptography. But before getting there, it helps to look at two protocols that showcase how entanglement reshapes communication. One of these is quantum teleportation. Despite the name, no object is transported and nothing moves faster than light. What is transferred is a quantum state. In a teleportation protocol, two parties, often called Alice and Bob, begin by sharing an entangled pair of qubits. Alice also possesses a third qubit in an unknown state that she wishes to transfer to Bob. By performing a joint measurement on her two qubits and sending the result to Bob using an ordinary classical channel, Alice enables Bob to reconstruct the original state on his qubit. The original state does not survive the process. It is destroyed when Alice performs her measurement. No additional copy is created. The transfer relies on both shared entanglement and classical communication. Without either, it cannot work. Teleportation does not violate causality or allow faster-than-light signaling. It respects every constraint imposed by relativity. There is also a protocol that works in the opposite direction, called superdense coding. Here again, Alice and Bob begin by sharing an entangled pair. Alice then performs one of several possible operations on her qubit and sends it to Bob. By measuring the two qubits together, Bob can extract more classical information than would normally be possible from a single qubit. Specifically, one qubit sent from Alice to Bob can carry two classical bits of information, provided entanglement is available in advance. This does not contradict any limits, because the entanglement itself was a resource established earlier. The protocol simply shows how quantum correlations can be used to pack information more efficiently than classical correlations allow. These examples hint at the deeper promise of quantum computing. A quantum computer is a device that processes information using qubits, quantum gates, and measurements. The computation proceeds by preparing an initial quantum state, applying a sequence of controlled operations, and finally measuring to extract a result. The key to quantum computing is not that it tries all answers at once. That is a common but misleading description. The real power comes from interference. A quantum algorithm is designed so that unwanted computational paths cancel each other out, while desired paths reinforce one another. The final measurement then has a high probability of yielding the correct answer. One of the most famous examples is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. Factoring is the basis of widely used cryptographic schemes, and Shor's results showed in principle that a sufficiently powerful quantum computer could break them. Another example is Grover's algorithm, which searches an unsorted database quadratically faster than any classical method. The speedup is not exponential, but it is provably optimal. No quantum algorithm can do better for that problem. These algorithms do not rely on vague parallelism. They rely on precise control of amplitudes and phases. They work only if coherence is maintained and interference is carefully engineered. This makes quantum computation extremely sensitive to noise. Real qubits are not isolated. They interact with their environment. Decoherence and operational errors corrupt quantum information. Left uncorrected, these errors quickly overwhelm any computation. Quantum error correction provides a way forward. At first glance, it seems impossible. How can errors be corrected if quantum states cannot be copied and measurement disturbs them? The solution is subtle and ingenious. Instead of encoding information into a single physical qubit, quantum error correction spreads it across many qubits using entanglement. The logical information is stored non-locally. Carefully chosen measurements, called syndrome measurements, can detect the presence and type of errors without revealing the encoded quantum information itself. Once an error is detected, corrective operations can be applied to restore the intended state. This process can be repeated continuously, allowing quantum information to be stabilized even in noisy environments. One of the leading approaches is known as the surface code. In this scheme, qubits are arranged on a two-dimensional grid, and the logical information is encoded in global properties of the system rather than local details. Errors must accumulate along extended paths to cause failure, which makes the code remarkably robust. The protection is often described as topological, because it depends on the global structure rather than local fluctuations. Quantum cryptography brings these ideas back to communication. One of the earliest and simplest protocols is known as BB84. In this scheme, Alice sends qubits to Bob prepared in randomly chosen bases. Bob measures them in randomly chosen bases as well. Later, Alice and Bob compare which bases they used and keep only the cases where they matched. If an eavesdropper tries to intercept the qubits and copy them, the no-cloning theorem guarantees that errors will be introduced. These errors can be detected statistically. The security of the protocol does not rely on assumptions about computational difficulty. It relies directly on the laws of physics. More advanced schemes go even further. Device-independent quantum key distribution removes the need to trust the internal workings of the devices themselves. Security is certified by observing violations of Bell inequalities. If the correlations are strong enough, then no eavesdropper, no matter how powerful, could have intercepted the information without being detected. This is a striking idea. Security guaranteed not by secrecy or complexity, but by the structure of reality. Quantum information theory has reshaped how quantum mechanics is understood. It treats entanglement as a resource. It reframes uncertainty and measurement as constraints on information flow. It connects abstract principles to operational tasks. It has also influenced other areas of physics. Concepts like entanglement entropy now play central roles in condensed matter physics, quantum field theory, and even approaches to quantum gravity. Information has become a unifying language. At the same time, quantum information highlights the limits of what is possible. No cloning, no faster than light signaling, no perfect isolation. These are not inconveniences, they are the rules of the game. Quantum computers are difficult to build not because the ideas are unclear, but because nature is unforgiving. Coherence must be protected. Errors must be managed. Control must be precise. Progress is steady, but challenging. Whether large-scale quantum computers will ultimately transform computation remains an open question. What is already clear is that quantum information has transformed understanding. It has shown that quantum mechanics is not just a theory of particles and waves, but a theory of information itself. In that sense, quantum information does not add something new to quantum mechanics. It reveals what was already there, waiting to be noticed. No quantum system exists in perfect isolation. Even the most carefully engineered experiment is embedded in an environment, and that environment is never completely silent. Stray electromagnetic fields, thermal radiation, vibrations, surrounding particles and internal degrees of freedom all exert some influence. These interactions may be weak or strong, slow or fast, but they are always present. Once a system interacts with its surroundings, its behavior changes in systematic ways. Phase relationships between components of the quantum state are degraded, a process known as decoherence. Energy can leak into or out of the system, which is called dissipation. Over longer times, the system may approach a thermal equilibrium state determined by its environment. These effects are not accidents. They are unavoidable consequences of coupling to external degrees of freedom. To describe such situations, the wave function alone is no longer sufficient. The appropriate language is the density matrix, which can track both quantum coherence and statistical uncertainty. For open systems, the density matrix does not evolve according to the simple, reversible Schrodinger equation. Instead, its evolution reflects both the system's internal dynamics and the continual influence of the environment. In many physically relevant cases, the environment acts in a memoryless way. Each interaction affects the system, but the environment does not retain detailed information that feeds back later. This regime is called Markovian. When this approximation is valid, the evolution of the density matrix is governed by a specific type of equation known as the Lindblad equation. The Lindblad equation is a master equation. It gives the rate of change of the density matrix as the sum of two contributions. One is the familiar Hamiltonian term, which describes the unitary, reversible part of the evolution. The other consists of additional terms that encode the effects of the environment. These additional terms involve operators often called jump operators. Each one represents a particular way the system can exchange information or energy with its surroundings. Some jumps correspond to energy loss, such as the emission of a photon. Others correspond to dephasing, where relative phases are randomized without changing energy. The precise form of these operators depends on the physical nature of the coupling. What makes the Lindblad equation especially important is not just what it describes, but what it guarantees. Its structure ensures that the density matrix remains physically valid at all times. Probabilities stay positive. The total probability remains equal to 1. No unphysical states are produced. This consistency is not automatic. It requires a very specific mathematical form, and the Lindblad equation is essentially the most general evolution that satisfies these requirements under the Markovian assumption. The result is a powerful and widely used framework. It underlies the theoretical description of atomic decay, laser cooling, superconducting circuits, quantum optics, and many other systems where environmental effects cannot be ignored but are still well controlled. However, the Lindblad equation describes an average. It tells you how the density matrix evolves when you consider many experimental runs and average over them. It does not directly describe what happens in a single run of an experiment, especially if the environment is being continuously monitored. To understand individual experimental records, another perspective is useful. This is provided by quantum trajectory methods. Imagine an open quantum system coupled to an environment that is being observed, perhaps through photon detectors or other monitoring devices. In each run of the experiment, the environment produces a specific sequence of detection events, or perhaps no detections at all. Given this measurement record, the state of the system evolves in a way that is both continuous and punctuated by sudden changes. Quantum trajectory methods describe this evolution. Instead of a smooth, deterministic equation for the density matrix, the system follows a stochastic path. Most of the time, the state evolves smoothly according to an effective non-Hermitian Hamiltonian. Occasionally a jump occurs, corresponding to a detected interaction with the environment. Each jump updates the state abruptly. Each individual trajectory represents one possible history of the system, conditioned on what was observed in the environment. Different runs produce different trajectories. When these trajectories are averaged together, the result reproduces the Lindblad equation for the density matrix. In this sense, the master equation emerges as a statistical average over many possible underlying histories. This picture provides a more intuitive link between continuous measurement and open system dynamics. It shows how randomness enters not as a vague disturbance, but as a consequence of conditioning on partial information. The environment is constantly acquiring information about the system. Monitoring the environment turns that information into a concrete record, and the system's state updates accordingly. Quantum trajectories are not just a mathematical trick. They are directly relevant to experiments where continuous monitoring is essential. In quantum optics, individual photon emissions can be tracked. In superconducting circuits, microwave signals leaking from resonators can be measured in real time. In these settings, the trajectory picture matches what is actually seen in the lab. Open system theory also clarifies the relationship between decoherence and dissipation. Decoherence can occur even when little or no energy is exchanged. A system can lose phase coherence simply because information about its state leaks into the environment. Dissipation, by contrast, involves energy flow. Both processes can occur together, but they are conceptually distinct and often occur on different timescales. Thermalization adds another layer. When a system interacts with a large environment at a fixed temperature, it often relaxes toward a thermal state. This process can be described within the same framework, with appropriate jump operators and rates. The approach to equilibrium is not imposed by hand. It emerges from repeated interactions with many environmental degrees of freedom. What makes open quantum systems particularly interesting is that they sit at the boundary between the quantum and classical worlds. Decoherence explains why interference disappears. Dissipation explains why energy relaxes. Continuous monitoring explains how classical records arise from quantum processes. Together, these ideas show that classical behavior is not something added on top of quantum mechanics. It emerges from it when isolation fails. At the same time, open system theory reveals new possibilities. By carefully engineering environments, it is sometimes possible to protect quantum states rather than destroy them. Certain forms of dissipation can stabilize entanglement or drive systems into desired states. In this way, the environment becomes a tool rather than an enemy. This perspective has reshaped how quantum experiments are designed. Instead of fighting every interaction, researchers increasingly try to control them. Noise is characterized, couplings are shaped, and decoherence is managed rather than simply minimized. Open systems remind us that quantum mechanics was never meant to describe idealized objects floating in isolation. It was always a theory of interaction, probability, and information. When environments are included explicitly, the theory becomes richer, not weaker. The loss of coherence, the flow of energy, and the emergence of classical behavior are not failures of quantum mechanics. They are among its most successful explanations. Understanding open systems does not make quantum mechanics less strange, it makes it more complete. Quantum optics is the branch of quantum mechanics that treats light itself as a quantum system. It takes the electromagnetic field, which in classical physics is described as a smooth wave filling space, and applies the full machinery of quantization to it. The result is a picture of light that is both elegant and deeply non-classical. In quantum theory, the electromagnetic field is not made of particles moving through space in the ordinary sense. Instead, it is a field with quantized excitations. These excitations are what are called photons. A photon is not a tiny billiard ball of light. It is a discrete packet of energy associated with a specific mode of the electromagnetic field. Each mode of the field, defined by a particular frequency and spatial pattern, behaves mathematically like a quantum harmonic oscillator. This is a remarkable and powerful result. Just as a mass on a spring has quantized energy levels in quantum mechanics, so does each mode of the electromagnetic field. The allowed energy levels are equally spaced, and the number of excitations in a mode is called the photon number. 0 photons corresponds to the vacuum state of that mode, not empty nothingness, but a state with well-defined quantum fluctuations. This framework explains why light sometimes behaves like a wave and sometimes like particles. Wave behavior arises from the coherent superposition of many photon states. Particle behavior emerges when energy is exchanged in discrete amounts. Among all possible quantum states of light, there is one class that comes closest to classical intuition. These are called coherent states. A coherent state is what is produced approximately by a well-stabilized laser. In a coherent state, the electromagnetic field has a well-defined phase and oscillates in a way that closely follows the classical field equations on average. The photon number in such a state is not fixed. Instead, it follows a Poisson distribution. This means that the number of photons fluctuates, but in a very specific and predictable way. The relative fluctuations become small when the average photon number is large, which is why bright laser light appears so stable. Coherent states are often described as the most classical states of light, but that phrase should be used carefully. They're still fully quantum states. They still exhibit quantum noise. They still obey uncertainty relations. What makes them special is that their uncertainties are balanced in a way that mimics classical behavior as closely as quantum mechanics allows. Quantum optics becomes especially interesting when light is prepared in states that have no classical analogue at all. These are called non-classical states of light. Examples include single photon states, squeezed states, and entangled photon pairs. A single photon state is exactly what it sounds like. There is precisely one excitation in a given field mode. Such a state cannot be described as a wave with fluctuating amplitude. It is inherently discrete. When measured, it delivers its energy in a single indivisible event. One way to reveal the non-classical nature of light is through photon statistics. Classical light sources tend to produce photons that arrive in clumps, a phenomenon known as bunching. In contrast, single photon sources exhibit anti-bunching. Photons avoid arriving together. Detecting one photon suppresses the probability of detecting another immediately afterward. This behavior cannot be explained by any classical wave model. Another striking effect is known as the Hongou-Mandel effect. Imagine two identical photons entering a beam splitter from different input ports at exactly the same time. Classical reasoning might suggest that each photon randomly chooses an output port. That is not what happens. Instead, the two photons always exit together through the same port. They never split. This effect arises from quantum interference between indistinguishable processes. It provides a direct experimental test of photon indistinguishability and has become a standard tool in quantum optics and quantum information experiments. Quantum optics also studies the interaction between light and matter in regimes where both must be treated quantum mechanically. One of the most important settings for this is cavity quantum electrodynamics. In a cavity experiment, an atom or other quantum emitter is placed inside a cavity formed by highly reflective mirrors. The cavity supports discrete electromagnetic modes, and if the coupling between the atom and one of these modes is strong enough, energy can be exchanged coherently between them. In this strong coupling regime, the atom and the field do not behave as separate systems. They form a combined quantum system that oscillates back and forth between atomic excitation and photon excitation. These oscillations are called vacuum-Rabi oscillations, and they occur even when the cavity initially contains no photons. The vacuum itself plays an active role. The simplest theoretical description of this situation is known as the Jaynes-Cummings model. It describes a two-level atom coupled to a single mode of the electromagnetic field. Despite its simplicity, it predicts a rich set of phenomena, including collapses and revivals of atomic excitation and highly non-classical states of light. Many of these predictions have been confirmed experimentally with remarkable precision. Another powerful class of non-classical states is squeezed light. Squeeze states exploit the fact that the electromagnetic field has multiple complementary components, often called quadratures, analogous to position and momentum. In a coherent state, the uncertainties in these quadratures are balanced and minimal. In a squeeze state, the uncertainty in one quadrature is reduced below the level found in coherent light, at the cost of increased uncertainty in the other. This trade-off respects the uncertainty principle, but redistributes the noise in a useful way. Squeezed light is not just a laboratory curiosity, it has real applications in precision measurement. One of the most famous examples is gravitational wave detection. In interferometers such as LIGO, quantum noise in the light field limits sensitivity. By injecting squeezed light into the interferometer, it is possible to reduce this noise in the relevant quadrature and improve sensitivity beyond what would otherwise be possible. This allows detection of incredibly small space-time distortions, far smaller than the diameter of a proton. What makes quantum optics especially powerful is its experimental accessibility. Photons are easy to generate, manipulate, and detect with high precision. Optical systems can be well isolated from thermal noise. Individual quantum events can be observed directly. As a result, quantum optics has served as a testing ground for many foundational ideas in quantum mechanics. It has also become a cornerstone of quantum technology. Quantum communication, quantum cryptography, and many quantum computing architectures rely on optical systems. Entangled photons carry information across long distances. Cavities and waveguides mediate interactions. Optical measurements provide high-fidelity readout. At the same time, quantum optics continues to deepen understanding of light itself. It reveals that the vacuum is active, that noise has structure, and that classical electromagnetic waves emerge as special cases of much richer quantum behavior. Light, which once seemed the most classical of phenomena, turns out to be one of the most revealing windows into the quantum world. Quantum optics does not replace classical electromagnetism. It contains it. In regimes of large photon numbers and weak correlations, classical waves re-emerge naturally. But when individual quanta matter, when correlations are strong, or when precision approaches fundamental limits, the quantum nature of light becomes unavoidable. In that sense, quantum optics is not a niche subject. It is the place where the abstract principles of quantum mechanics become visible, controllable, and useful. It shows with exceptional clarity how the quantum and classical descriptions of the world fit together, and where the seams between them truly lie. One of the most profound ways quantum mechanics departs from classical thinking concerns the idea of identity itself. In everyday experience, objects remain distinct even when they appear identical. Two coins may look the same, but they can still be tracked, labelled, and distinguished by their histories. Quantum mechanics does not permit this view. At a fundamental level, identical quantum particles cannot be told apart at all. For identical particles, there is no physical meaning to labelling one as this particle and another as that particle. Exchanging two identical quantum particles does not create a new situation. It leaves the physical state unchanged. The theory treats the swapped configuration as exactly the same reality. This requirement leads to a strict mathematical rule. When identical particles are exchanged, the quantum state describing them must behave in one of only two allowed ways. It can either remain unchanged, or it can change sign. If the state is unchanged under exchange, the particles are called bosons. If the state changes sign, the particles are called fermions. In three-dimensional space, no other possibilities exist. From this simple distinction, far-reaching consequences follow. Bosons are particles with integer spin. Photons belong to this class, as do force carriers like gluons and certain composite particles such as some atoms. Because their states are symmetric under exchange, there is no restriction on how many bosons can occupy the same quantum state. They readily accumulate together. Fermions, by contrast, have half-integer spin. Electrons, protons, and neutrons are fermions. Their states are antisymmetric under exchange, and this antisymmetry has a dramatic consequence. If two identical fermions attempt to occupy the same quantum state, the state vanishes. It is not forbidden by force or repulsion, it simply does not exist. This fact is known as the Pauli exclusion principle. It states that no two identical fermions can share the same quantum state. It is not an interaction and not a dynamical effect. It follows purely from symmetry. Exclusion underlies the structure and stability of matter. Without it, electrons would all collapse into the lowest energy state around atomic nuclei. There would be no atomic shells, no chemistry, and no periodic table. Matter would be radically different and unstable. Because electrons are fermions, they must occupy distinct quantum states. As lower energy states fill, additional electrons are forced into higher energy configurations. This layered structure gives rise to atomic shells and ultimately determines chemical behavior. Exclusion also explains why matter resists compression. In extreme environments such as white dwarf stars, electrons are packed so densely that all low-energy states are filled. Further compression would require electrons to occupy very high momentum states, which costs enormous energy. The resulting pressure, known as degeneracy pressure, can counteract gravity and support a star. This effect has nothing to do with temperature. It is purely quantum mechanical. In ordinary materials, exclusion shapes electrical properties. In metals, electrons fill available states up to a characteristic energy level, forming what is known as a Fermi sea. Whether a material conducts electricity, insulates, or behaves as a semiconductor depends on how these fermionic states are filled and how electrons can transition between them. Bosons behave in a fundamentally different way. Because they are allowed to share quantum states, they can act collectively. At sufficiently low temperatures, a gas of bosons can undergo a transition known as Bose-Einstein condensation. In this phase, a large number of particles occupy the same lowest energy state. Their individual wave functions overlap, and the system behaves as a single coherent quantum object. The entire condensate is described by one shared quantum state. This phenomenon was predicted early in quantum theory but observed only much later, once techniques for cooling atoms to extremely low temperatures became available. When it occurs, quantum behavior becomes visible on macroscopic scales. Matter waves interfere. Coherence extends across the entire system. Related collective effects appear in other exotic states of matter. One example is superfluidity, in which a fluid flows without viscosity below a critical temperature. Such a fluid can climb walls, flow through tiny channels, and sustain motion indefinitely without slowing. Superfluidity arises because the fluid occupies a coherent quantum state. Energy dissipation is suppressed, flow becomes quantized, and vortices appear only with specific discrete circulation values. These vortices are not defects. They are required by the quantum structure of the state. Another closely related phenomenon is superconductivity. In a superconductor, electrical current flows with zero resistance. This effect does not arise because electrons move freely as individuals. It occurs because electrons form pairs. Although electrons repel each other and are subject to exclusion, under suitable conditions they can bind indirectly through interactions with vibrations of the crystal lattice. These bound pairs are called Cooper pairs. Each pair consists of two fermions, but together they behave as a boson. As bosonic objects, Cooper pairs can condense into a collective quantum state. Once this happens, electrical current flows without scattering, and resistance disappears. The theoretical explanation of this process is given by Bardeen-Cooper-Schrieffer theory, which shows how a weak attractive interaction mediated by lattice vibrations can produce a superconducting phase. Superconductivity reveals itself through striking effects. Magnetic fields are expelled from the interior of a superconductor. Electrical currents persist indefinitely. Quantum coherence extends across macroscopic distances. This coherence is vividly demonstrated in Josephson junctions, where two superconductors are separated by a thin barrier. Cooper pairs tunnel through the barrier, producing a current that depends on the relative phase of the superconducting states. This effect is exquisitely sensitive and forms the basis of some of the most precise measurement technologies available. What unites all of these phenomena is statistics rather than force. The distinction between bosons and fermions arises from symmetry under exchange, and that distinction alone reshapes the behavior of matter across every scale. Indistinguishability in quantum mechanics is exact. It is not an approximation or a convenience. If particles are identical in all physical properties, then the theory does not allow them to be labelled, even in principle. Attempting to do so leads to predictions that contradict experiment. This is why quantum statistics cannot be ignored or replaced by clever accounting. It is enforced by the structure of the theory itself. In certain two-dimensional systems, even more exotic behavior appears. Particles known as anyons can obey statistics that are neither purely bosonic nor fermionic. These particles arise in quantum Hall systems and are being explored for use in fault-tolerant quantum computation, revealing deep connections between dimensionality, statistics, and topology. Even without these exotic cases, the impact of quantum statistics is already everywhere. The stability of matter, the diversity of chemistry, the behavior of stars, the properties of metals, and the existence of superconductors all depend on it. Classical physics has no analogue of this principle. In a classical world, particles are always distinguishable. Quantum mechanics replaces that assumption with something stricter and more powerful. Identical particles are not individuals with separate identities. They are excitations of underlying fields. What matters is not which particle is where, but how many particles occupy which states. This shift can feel unsettling, but it is also deeply unifying. It shows how much of the structure of the physical world arises from simple abstract rules applied consistently. Quantum statistics does not add unnecessary strangeness to physics. It explains why matter has structure at all. Without it, the universe would look nothing like the one that exists. At some point, ordinary quantum mechanics runs into a fundamental limitation. It works beautifully for systems with a fixed number of particles, evolving smoothly in time. But the real universe does not behave that way. Particles are created and destroyed. High-energy collisions produce entirely new particles. Radiation can turn into matter, and matter can turn back into radiation. Trying to force these processes into a framework built around a fixed particle count quickly becomes awkward. Quantum field theory resolves this by changing what is considered fundamental. Instead of treating particles as the basic entities, it treats fields as primary. Particles are no longer objects that persist through time. They are excitations of underlying quantum fields. In this picture, every type of particle corresponds to a field that exists everywhere in space. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Creating a particle means exciting a field. Destroying a particle means de-exciting it. This shift makes particle creation and annihilation completely natural. Quantum field theory also fits comfortably with special relativity. Relativity demands that no signal travels faster than light, and that space and time are treated on equal footing. Fields, rather than particles with fixed identities, provide the right language for this. Interactions become local interactions between fields at space-time points, preserving causality automatically. The simplest and most successful example of this framework is quantum electrodynamics, often abbreviated as QED. This is the quantum field theory that describes electromagnetic interactions. It includes the electron field, the positron field, and the photon field, along with precise rules for how they interact. In QED, processes like scattering, emission, absorption, and pair creation are described as interactions between fields. An electron emitting a photon is not a particle tossing out another particle. It is a field interaction that transfers energy and momentum in discrete amounts. What makes QED especially remarkable is its accuracy. It is the most precisely tested theory in the history of science. One famous example is the magnetic moment of the electron. Quantum field theory predicts a tiny deviation from the simple classical value, arising from interactions with virtual fluctuations of the electromagnetic field. This prediction matches experimental measurements to roughly 10 significant figures. Few, if any, theories have ever been tested so stringently. To perform calculations in quantum field theory, physicists often use a graphical shorthand known as Feynman diagrams. These diagrams are not pictures of what literally happens in space and time. They are visual representations of terms in a mathematical expansion. In a Feynman diagram, lines represent propagators, which encode how fields transmit influence between space-time points. Vertices represent interactions, where fields couple to one another. Each diagram corresponds to a specific mathematical expression that contributes to the overall probability amplitude for a process. It is important not to take these diagrams too literally. The internal lines in a diagram are not particles flying around unseen. They are intermediate mathematical terms in an integral. They do not satisfy the usual relationship between energy and momentum that real particles do. Calling them virtual particles is convenient shorthand, but it can be misleading if taken too seriously. Feynman diagrams are bookkeeping tools. Their power lies in organizing complex calculations into manageable pieces. They make it possible to compute scattering probabilities, decay rates, and radiative corrections systematically. However, early attempts at quantum field theory ran into a serious problem. Straightforward calculations often produced infinities. Predicted quantities such as mass and charge appeared to diverge without bound. This was not just a technical nuisance, it threatened the internal consistency of the theory. The resolution of this problem is known as renormalization. At first glance, renormalization can seem like a mathematical trick. In reality, it reflects a deep physical insight. The key idea is that quantities like mass and charge are not fixed, absolute numbers. They depend on the energy scale at which they are measured. When a particle is probed at very high energy, it interacts with quantum fluctuations of the fields around it. These fluctuations modify the effective values of its properties. Renormalization provides a systematic way to account for this. The infinities that appear in naive calculations are absorbed into a redefinition of parameters. What remains are finite, well-defined predictions for observable quantities. As the energy scale changes, the effective parameters run, meaning they change smoothly with scale. This running of parameters is not an embarrassment. It is a prediction. It has been confirmed experimentally in many contexts, especially in high-energy particle physics. Renormalization tells us that physical theories are effective descriptions, valid over certain ranges of energy, rather than immutable laws with fixed constants. The most comprehensive application of quantum field theory is the Standard Model of particle physics. This framework describes all known fundamental particles and forces, with one notable exception. Gravity is not included. In the Standard Model, matter comes in two basic categories. Quarks make up protons, neutrons, and other hadrons. Leptons include electrons, muons, tall particles, and their associated neutrinos. Each of these particles is an excitation of its own quantum field. Forces arise from interactions mediated by other fields. The electromagnetic force is mediated by photons. The weak force is mediated by the W and Z bosons. The strong force is mediated by gluons. The strong force is described by a quantum field theory called quantum chromodynamics, often abbreviated as QCD. It governs how quarks interact via color charge. One of its most striking features is asymptotic freedom. At very high energies, quarks interact weakly and behave almost like free particles. At low energies, the interaction becomes extremely strong, leading to confinement. Quarks are never observed in isolation. They are permanently bound into composite particles. Mass in the Standard Model has a subtle origin. Most particles do not have mass simply by assumption. Instead, they acquire mass through interaction with a field known as the Higgs field. When the Higgs field undergoes spontaneous symmetry breaking, particles that interact with it gain mass, while others remain massless. This mechanism was confirmed experimentally with the discovery of the Higgs boson. Quantum field theory does more than catalogue particles. It provides a unified language for understanding interactions, symmetries, and conservation laws. Gauge symmetries determine the form of interactions. Renormalization controls how theories behave across scales. Fields replace particles as the fundamental entities. At the same time, quantum field theory is not the final word. It is extraordinarily successful, but incomplete. Gravity remains outside the framework. Attempts to quantize gravity using the same methods run into deep difficulties. This signals that new ideas are needed. Even so, quantum field theory represents a profound synthesis. It combines quantum mechanics, special relativity, and symmetry into a single coherent structure. It explains why particles can be created and destroyed. It predicts phenomena with astonishing precision. It reveals that what appear to be elementary particles are better understood as excitations of deeper fields. In this picture, the vacuum itself is not empty. It is the lowest energy state of all fields combined. It seethes with fluctuations. It influences particle properties. It shapes what is possible. Quantum field theory replaces the idea of a universe built from tiny objects with one built from continuous fields and discrete excitations. Particles are events, not things. Interactions are local, but their consequences can be global. This shift can feel abstract, but it has proven to be one of the most productive ideas in modern physics. It underlies everything known about fundamental particles and forces. It has guided decades of experimental discovery. And despite its challenges, it remains the best description we have of the quantum world at its deepest level. If ordinary quantum mechanics teaches how systems evolve, quantum field theory teaches what those systems are made of. And what they are made of is not particles, but possibility structured by fields. Quantum mechanics is often presented as a collection of abstract ideas, but its influence is anything but abstract. The principles explored so far do not live only in equations or thought experiments. They appear wherever nature operates on small scales, and they quietly support technologies that define everyday life. One of the clearest examples is quantum tunneling. In classical physics, a particle encountering a barrier higher than its energy simply cannot cross it. The motion stops. Quantum mechanics tells a very different story. When a particle meets a barrier, its wave function does not abruptly vanish at the boundary. Instead, it penetrates into the barrier and decays gradually. If the barrier is thin enough, the wave function can extend all the way through. As a result, there is a real probability that the particle appears on the other side, despite never possessing enough energy to pass over the barrier in the classical sense. This effect is not rare or exotic. It explains alpha decay, where particles escape atomic nuclei by tunneling through the nuclear potential. It underlies tunnel diodes and many modern electronic components. It is also the operating principle of the scanning tunneling microscope, which images surfaces atom by measuring a tunneling current that depends sensitively on distance. Without tunneling, such instruments would be impossible. Quantum mechanics also reveals itself through striking collective effects, such as the quantum Hall phenomena. When electrons are confined to 2 dimensions, cooled to extremely low temperatures, and exposed to strong magnetic fields, their behavior reorganizes in a highly structured way. In the integer quantum Hall effect, the resistance measured perpendicular to the current takes on precisely quantized values. These values are exact. They do not depend on material imperfections, sample shape, or microscopic details. The quantization is so reliable that it serves as a practical standard for electrical resistance. The origin of this effect lies in topology. The electronic states are characterized by global quantities known as Chern numbers. These quantities cannot change smoothly. They shift only in discrete steps, locking physical observables to exact values. In these systems, electrical current flows along the edges of the material rather than through its interior. These edge states are remarkably robust. They resist scattering and carry current without dissipation, while the bulk of the material remains insulating. Even more surprising is the fractional quantum Hall effect. Here, strong interactions between electrons give rise to new collective states, whose excitations behave as particles carrying fractional electric charge. These quasiparticles obey unusual statistics that are neither purely bosonic nor fermionic. Known as anyons, they are of intense interest as possible building blocks for fault-tolerant quantum computation because their properties are protected against local disturbances. Quantum mechanics also reshapes the limits of precision measurement. There are fundamental constraints on how accurately quantities can be measured, but those limits depend on how measurements are performed. When many independent probes are used, uncertainty typically decreases with the square root of the number of probes. This scaling is known as the standard quantum limit and arises from unavoidable quantum noise. It is not a technological flaw. Quantum mechanics, however, allows probes to be correlated. When entanglement is introduced, noise can be redistributed in useful ways. In principle, this allows precision to improve more rapidly, reaching a scaling known as the Heisenberg limit. This improvement is not merely theoretical. Techniques based on squeezing and entanglement are already in use. Gravitational wave detectors employ squeezed light to suppress quantum noise. Atomic clocks exploit entangled atomic states to improve timekeeping. These advances rely on quantum effects with no classical equivalent. At very small scales, even thermodynamics must be reconsidered. Traditional thermodynamics assumes large systems and negligible fluctuations. Quantum systems violate both assumptions. In the quantum regime, fluctuations are unavoidable and often dominant. Measurements disturb systems. Quantities like work and heat become statistical rather than deterministic. New relationships are required to connect equilibrium behavior with non-equilibrium processes. One such relationship is the Jarzynski equality, which links the statistics of work performed during non-equilibrium transformations to equilibrium free energy differences. Remarkably, it remains valid even far from equilibrium. Quantum versions of this relation incorporate measurement effects and coherence, revealing deep connections between information and thermodynamics. Quantum thermodynamics also explores miniature heat engines whose working components may be single atoms, spins, or superconducting circuits. These systems raise fundamental questions. Can coherence enhance efficiency? Can entanglement function as a thermodynamic resource? What limits are imposed by control and measurement? These questions remain active areas of research. Another subtle but powerful concept is geometric phase. When a quantum system evolves and returns to its original physical state, it can acquire a phase determined not by the duration of the evolution, but by the path taken through the space of states. This geometric phase, often called the Berry phase, has measurable consequences. It can shift interference patterns and modify observable quantities. It reflects the geometry of state space rather than local forces. A closely related effect is the Aharonov-Bohm phenomenon. An electron moving through a region with no electromagnetic fields can still acquire a measurable phase shift if electromagnetic potentials are present elsewhere. This demonstrates that potentials, not just fields, play a direct physical role in quantum mechanics. The effect has been confirmed experimentally and is important in mesoscopic and nanoscale systems. Despite being more than a century old, quantum mechanics remains an active and evolving theory. Quantum computing aims to build fault-tolerant machines capable of solving problems inaccessible to classical computers. Progress continues, but challenges such as decoherence, noise, and scaling remain central obstacles. Quantum simulation uses well-controlled quantum systems, including cold atoms and trapped ions, to emulate complex many-body behavior. This approach provides insight into superconductivity, exotic phases of matter, and dynamics far from equilibrium. Foundational questions also persist. The measurement problem has not been settled to universal agreement. Competing interpretations remain. Some propose subtle modifications of the theory that could be experimentally tested, and designing such tests is an ongoing effort. Perhaps the most profound challenge lies in reconciling quantum mechanics with gravity. General relativity treats spacetime as dynamic, while quantum mechanics assumes a fixed temporal background. Bridging this divide has proven extraordinarily difficult. Approaches such as quantum gravity, string theory, and loop quantum gravity attempt to address it, but a complete and confirmed theory remains out of reach. What stands out is not that questions remain, but that quantum mechanics continues to function with extraordinary accuracy across vast scales. From atoms to stars, from microchips to gravitational wave detectors, these same principles apply. Quantum mechanics is not fragile, it is robust. It survives relentless experimental scrutiny and continues to deliver reliable predictions. Where it feels strange, it is not because it fails, but because it challenges classical intuition. The effects described here are not peripheral curiosities. They are what emerges when the theory is taken seriously and followed to its consequences. Tunneling, topology, entanglement, coherence, and geometry are not optional features. They are woven into the structure of the quantum world. The open questions at the edges of quantum mechanics are not signs of weakness. They are signs of depth. A theory that remains productive after more than a century is not nearing completion. It is still unfolding. Quantum mechanics does not promise comfort. It promises accuracy, and again, it fulfills that promise.